Hello and welcome. In this video, we'll be exploring the fascinating world of transforming functions. By the end of this session, you will be able to describe and apply three fundamental types of transformations: translations, stretches, and reflections. We'll learn how to manipulate the graph of a function by changing its equation, and we'll see how these changes affect the coordinates of points on the graph. Let's begin with a familiar function, our base function, which we'll call f of x. For our first example, let's use the cubic function f of x equals x cubed minus 8. Here is its graph. Notice it passes through the point 2, 0, and has an inflection point at 0, minus 8. Our goal is to understand how to change this graph into a new one, g of x, by applying transformations. Let's start with the simplest type, translations. First up, we have translations. A translation is a slide or shift of the graph without changing its shape or orientation. We'll look at two types, vertical and horizontal translations. Let's start with vertical translations. These are controlled by adding or subtracting a constant outside the function. The general form is y equals f of x plus b, where b is a constant. If b is positive, the graph moves up. If b is negative, it moves down. The entire graph shifts vertically by b units. Let's see this in action with our base function f of x equals x cubed minus 8. Consider the function g of x equals f of x plus 2. This means g of x equals x cubed minus 8 plus 2, which simplifies to x cubed minus 6. As you can see, the graph of g of x is identical to f of x, but it has been shifted upwards by 2 units. The point 0 minus 8 on f of x moves to 0 minus 6 on g of x. Now let's try g of x equals f of x minus 3. This is x cubed minus 8 minus 3, which is x cubed minus 11. This time, the graph shifts downwards by 3 units. The point 0 minus 8 moves to 0 minus 11. So adding a constant outside the function translates the graph vertically. Now let's explore horizontal translations. These are a bit counterintuitive, so pay close attention. The general form is y equals f of x minus a, where the constant a is inside the function, affecting the x value. Here's the key. If a is positive, the graph moves to the right. If a is negative, it moves to the left. It's the opposite of what you might expect. Let's use our base function again, f of x equals x cubed minus 8. Consider g of x equals f of x minus 4. This means we replace every x in f of x with x minus 4. So g of x equals the quantity x minus 4 cubed minus 8. Notice that the graph has shifted 4 units to the right. The point 2, 0 on f of x moves to 6, 0 on g of x. Now let's try g of x equals f of x plus 1. Remember, this is f of x minus negative 1, so a is negative 1. The graph should move to the left. And it does. The graph shifts 1 unit to the left. The point 2, 0 moves to 1, 0. So subtracting a constant inside the function translates the graph horizontally. We can combine these translations into a single transformation. The general form for a combined translation is y equals f of x minus a, comma, plus b. This translates the graph a units horizontally and b units vertically. We can represent this as a translation vector. The translation vector is a column matrix with a on top and b on the bottom. This vector tells us how much to shift the graph. Let's work through an example. Suppose we have the function f of x equals x squared, and we want to find the equation of the function g of x that results from translating f of x by the vector 3 minus 4. The vector 3 minus 4 means we shift 3 units to the right and 4 units down, so a equals 3 and b equals minus 4. Plugging these values into our general form, we get g of x equals f of x minus 3 minus 4. Since f of x is x squared, f of x minus 3 is the quantity x minus 3 squared. So g of x equals x minus 3 squared minus 4. We can expand this to get the final form. G of x equals x squared minus 6x plus 5. This is the equation of the translated parabola. Now let's move on to our second type of transformation, stretches. A stretch changes the shape of the graph by scaling it. Like translations, we have two types, vertical and horizontal stretches. Let's start with vertical stretches. These are controlled by multiplying the entire function by a constant. The general form is y equals p times f of x, where p is a positive constant called the scale factor. If p is greater than 1, the graph is stretched away from the x-axis. If p is between 0 and 1, the graph is compressed towards the x-axis. Let's use f of x equals x squared as our base function. Consider g of x equals 2 times f of x. This is g of x equals 2x squared. As you can see, the graph of g of x is narrower than f of x. It has been stretched vertically by a scale factor of 2. Every y-coordinate is doubled. Now let's try g of x equals 1/2 f of x. This is g of x equals 1/2 x squared. This time, the graph is wider. It has been compressed vertically by a scale factor of 1/2. Every y-coordinate is halved. So multiplying the function by a constant stretches it vertically. Next, let's look at horizontal stretches. These are also a bit counterintuitive. The general form is y equals f of qx, where q is a positive constant. The scale factor for a horizontal stretch is not q, but 1 over q. If q is greater than 1, the graph is compressed horizontally. If q is between 0 and 1, the graph is stretched horizontally. Let's use f of x equals x squared again. Consider g of x equals f of 2x. This means we replace every x in f of x with 2x. So, g of x equals the quantity 2x squared, which simplifies to 4x squared. The graph of g of x is narrower. It has been compressed horizontally by a scale factor of 1/2. Every x-coordinate is halved. Now let's try g of x equals f of 1/2 x. This is g of x equals the quantity 1/2 x squared, which is 1/4 x squared. This time the graph is wider. It has been stretched horizontally by a scale factor of 2. Every x-coordinate is doubled. So multiplying x by a constant inside the function stretches it horizontally. Our final type of transformation is reflections. A reflection flips the graph across an axis. We'll look at two types, reflection in the x-axis and reflection in the y-axis. Let's start with reflection in the x-axis. The general form is y equals negative f of x. This transformation changes the sign of every y-coordinate. Let's use f of x equals x cubed minus 2. Consider g of x equals negative f of x. This is g of x equals negative of the quantity x cubed minus 2, which simplifies to negative x cubed plus 2. As you can see, the graph of g of x is the mirror image of f of x across the x-axis. The point 0, minus 2 moves to 0, 2. So multiplying the function by negative 1 reflects it in the x-axis. Now for reflection in the y-axis. The general form is y equals f of negative x. This transformation changes the sign of every x-coordinate. Let's use f of x equals e to the power of x. Consider g of x equals f of negative x. This is g of x equals e to the power of negative x. The graph of g of x is the mirror image of f of x across the y-axis. The point 0, 1 is an invariant point, meaning it doesn't move. So replacing x with negative x reflects the graph in the y-axis. Now that we've covered the basic transformations, let's see how to apply them to a specific point on a graph. Suppose we have a point x, y on the graph of y equals f of x. We want to find its new coordinates after a transformation. Let's consider a combined transformation. Y equals 3 plus 2 times f of 1/2 x plus 1. This looks complicated, but we can break it down. The key is to rewrite the expression inside the function to isolate the transformation. We can factor out 1/2 from the term 1/2 x plus 1. This gives us 1/2 times the quantity x plus 2. So our transformation is y equals 3 plus 2 times f of 1/2 times x plus 2. Now we can identify the transformations. The Dokolo, do, bo inside the function means a horizontal translation of 2 units to the left. The 1/2 inside means a horizontal stretch by a scale factor of 2. The 2 outside means a vertical stretch by a scale factor of 2. And the +3 outside means a vertical translation of 3 units up. Let's apply these to a point x, y. First, the horizontal translation. X becomes x minus 2. Then the horizontal stretch. X minus 2 becomes 2 times the quantity x minus 2. Next, the vertical stretch. Y becomes 2y. Finally, the vertical translation. 2y becomes 2y plus 3. So the new point is 2x dash 4, 2y plus 3. Let's try a specific point. If the point 1 minus 3 is on f of x, its new coordinates will be 2 times 1 minus 4 and 2 times negative 3 plus 3. This gives us negative 2, negative 3. So the point 1 minus 3 moves to minus 2, minus 3. Let's recap what we've learned today. We've explored 3 fundamental types of transformations. First, translations, which shift the graph. Vertical translations are of the form f of x plus b, and horizontal translations are of the form f of x minus a. Second, stretches, which scale the graph. Vertical stretches are of the form p times f of x, and horizontal stretches are of the form f of qx. Third, reflections, which flip the graph. Reflection in the x-axis is y equals negative f of x, and reflection in the y-axis is y equals f of negative x. We also saw how to combine these transformations and how to find the new coordinates of a point after a transformation. You are now able to describe and apply these transformations. To solidify your understanding, here are 5 practice questions. Pause the video, work through them, and then check your answers. Here are the answers. How did you do? Thank you for watching. Keep practicing these transformations, as they are a fundamental skill in higher-level mathematics.